Good morning, and it's nice to be back at Simon's in person after a lot of virtual events here. So I'll be talking about learning restricted Boltzmann machines, and this is based on joint work with Guy Bressler and Freddie Kohler. So my main interest in this talk will be understanding the algorithmic aspects of learning graphical models with latent variables. But first, I want to tell you about what's known about learning graphical models without latent variables. And even though I'm sure all of you know graphical models, please bear with me. Let's make sure we're on the same page in terms of notation. So graphical models are a rich model for defining high-dimensional distributions. And the important thing is, when you define them, you specify their dependent structure. So, a canonical example of this that's going to recur throughout this talk is an Ising model, which gives us a way to define a distribution on plus minus 1 to the n, which looks as follows. So we have variables capital X1 through Xn, and the probability of them taking on some realization little x is proportional to the exponential of some quadratic plus some linear function. So let's dig into this a little bit. So in fact, what we define is an n by n interaction matrix J that describes for each pair of variables I and j, whether they want to be the same or different signs. And that comes out through whether the entry in this interaction matrix is positive or negative. And the same way, we have this notion of an external field, which is in the absence of interactions. We can think about this vector little h as representing all of the individual biases. So the variables are not uniform over plus minus 1, but they might have some bias that depends on the strength and sign of this external field. Now, in order for this to be a distribution, it needs to be normalized. So the usual notation is that z is the normalizing constant, and it's called the partition function. And of course, this is really just the tip of the iceberg. So much beyond Ising models, you can talk about models over larger alphabets that takes you to things like the Potts model. You can also talk about models in which you have higher order interactions instead of just pairwise interactions. We'll talk more about that later, but roughly you can think about replacing what's happening in the exponent instead with a higher degree polynomial. So that way you might have 3y's or even higher order interactions. And of course, you could make it directed, in which case you could talk about things like Bayesian networks. Now, the important thing is that underneath this probability distribution is a graph, and that this graph captures the conditional independence structure. So the usual thing that we do is we take our distribution, and we define a graph on variables x1 through xn. And then we add edges for every pair of variables for which the corresponding entry in the interaction matrix is non-zero. So if these two variables have some sort of affinity where they want to agree or there's some sort of disagreement. And the important thing is that all of these familiar notions of graph theoretic notions of separation turn into notions of conditional independence of the associated distribution. So for example, if you have a pair of nodes I and j, and you have a subset U, well, if you have the graph theoretic property that all paths from I to j pass through the set U, so U is a separator for I and j, then it means that if you condition on all of the realizations of the variables in xu, that you get that I and j are conditionally independent. Yes?
Is this always the case, or do you have to make an assumption about the distribution being?
Yeah, so that's a great question. So this isn't an if and only if. What's true is that regardless of the way that I set the actual non-zero entries, this conditional independence property will be true. But I could have conditional independence properties where I have a conditional independence that's is not actually a separator in the graph theoretic sense. Yeah, that's right. So you need strictly positive, and we'll need that condition, but thank you. So the main question that I want to start off with before we get to the main topic of today is what about the algorithmic question about learning graphical models from samples? So what I'll mean by learning graphical models here is that you're going to assume some kind of upper and lower bounds on the interaction matrix and the external fields. But subject to those constraints, what you want to do is you want to learn the underlying graph theoretic structure. So this line of work goes way back. So it starts off with the work of Chow and Liu, who gave a polytime algorithm for learning graphical models, provided that the underlying graph is a tree. There's a much more recent work of Karger and Stein, where they gave a polynomial time algorithm that works on graphs of bounded tree width. Now, one of my favorite works in this sequence is this work of Guy Bressler, which was a very surprising result to me and to a few other folks, because what he did was he gave a polytime algorithm for learning graphs of bounded degree. So if the graph has degree at most d, then he gives an f of d times poly and n time algorithm. Now the f of d in front has a doubly exponential dependence on the degree. But what's really surprising about these results is that you can learn graphical models for which you can't actually sample from them if you had them. So he was actually learning it in a regime where the sampling and inference problems were known to be computationally hard. And these were improved in a sequence of works with Voufray et al. And Clivens and Mecca, where they improved the dependence on the degree, where the f of d just became singly exponential in d, and this is optimal. And of course, there are other threads of work on algorithms for learning graphical models, where the name of the game is you make some sort of stronger assumptions. They're usually assumptions that imply as a consequence things like the fact that your underlying graphical model does not have long-range correlations. In those cases, sometimes you can get better algorithms, maybe even things which are poly in D and poly in N. So my main goal today will be to try and understand what can we say algorithmically about learning graphical models, but with latent variables. And so the main question is really, the motivation for why you want to try and solve these kinds of things is that once you allow latent variables, it allows much more interesting phenomena. Because among the variables that you're observing, they can influence each other through unobserved mechanisms. So it's very scientifically important, for example, because if you have a bunch of observed data, maybe if I can find a parsimonious latent variable model that fits the data very well, that gives me some evidence that maybe this is a good scientific theory. So let me tell you about one particular latent variable model that's one of the simplest in this area, which is called the Restricted Boltzmann Machine. It's something that was popularized by Hinton in the 80s and 90s. And basically what you do is you take an Ising model, but it works on a bipartite graph. And one of the two sides in the bipartition is unobserved. So I have observed variables x1 through xn, and I have latent variables y1 through ym. And they're going to produce a joint distribution on plus minus 1 to the n cross plus minus 1 to the m. And the way that it works is that the observed variables only interact with the latent variables and vice versa. They still have the same types of external fields, but this in turn is itself an Ising model, which describes this joint distribution on x and y. But now the challenge is, even if this underlying Ising model is bounded degree, what happens if we don't observe all of the latent variables? So what happens if in this bipartite Ising model, there's an entire part in the partition that we don't see? How much does this confounding mess up our algorithms? So restricted Boltzmann machines are very important in machine learning. They have tons of applications and things like feature extraction, collaborative filtering. Actually, one of their claims to fame is that they were a building block of very early versions of deep learning. Because what you would do is you would take these restricted Boltzmann machines and you would stack them on top of each other as a way to create hierarchically more complicated probabilistic models. But the main question, which I'm going to be interested in, is, are there efficient algorithms for learning restricted Boltzmann machines? And there's going to be one key challenge, which is really going to stymie our attempts. Yeah.
So what exactly do you mean by learning them? Do you know existence of variables, or do you want to?
That's a great question, because learning the latent variables is going to be tricky because there are multiple latent variable models that are consistent with the data. For now, what I'll talk about is learning a description of the distribution on the observed nodes. But even then, you can ask for the proper learning problem of, can I go back and find an RBM that actually fits the data, even though you cannot uniquely determine what is the RBM that generated your data? So that's a great question. So in any case, let me tell you about the main technical challenge. This is a very simple thing to wrap your head around, which is that you can take this nice restricted Boltzmann machine, and once you marginalize out a single node, the trouble is that you end up with higher order dependencies. So what happens if I take an Ising model defined on this star graph, right? And I take the node in the middle and I marginalize it out. The trouble is that the corresponding induced distribution on these three leaves is no longer described by pairwise interactions because it's no longer an Ising model. It has a higher order interaction. So in fact, what type of distribution do we get when we take these simple Ising models and we marginalize out nodes? We get something, which I'll get into, which is called a Markov random field. So in particular, we'll be interested in binary Markov random fields, and a binary Markov random field of order R is just the distribution on plus minus 1 to the n, which has the same type of functional form that we've been talking about so far, but with the twist that this function that goes in the exponent is now a degree at most R polynomial. And the classic folklore fact is that if you take a restricted Boltzmann machine where all of the latent nodes, the ones that you're not going to be observing, if they have degree at most R, when you marginalize all of them out, what you will get is a distribution on the observed nodes that is itself a binary Markov random field of order at most R. So that's the classic fact. And one of the first questions we could ask is, okay, so maybe I can learn restricted Boltzmann machines just by treating them as Markov random fields and learning them that way. Now, I'll warn you that there's going to be a big catch to doing that, but let's dig into, what exactly is known about efficient algorithms for learning Markov random fields. So there's a work of Kleibens and Mecca and Hamilton et al., where they gave an algorithm which runs an n to the order r time for learning Markov random fields of order r, provided that the variables have bounded degree. Unfortunately, there's a bit of a computational problem here, which is that n to the r really is tight. So under standard hardness assumptions, you actually can't do better. The best running time for learning an order r Markov random field really is going to require n to the omega r time. And this is based on something called the sparse parity with noise hypothesis, just that learning a t-sparse parity with noise, which is one of the basic problems in computational learning theory, requires n to the omega t time. And so the idea is roughly that, order r Markov random fields are rich enough that they can capture things like sparse parity with noise. Even worse, they can capture them with bounded degree Markov random fields too. So let me try and refine the question that I care about. Yep. For this or for learning?
Is it the same method being used for both?
Well, one of the things that you can ask for learning for an order R Markov random field is you can ask, can I learn another Markov random field that produces a distribution that's close in TV, for example? But actually, a lot of these things work with even weaker notions of learning, namely improper learning, that it's hard even to learn a description of the underlying distribution that's close in TV. So I'll get to that a bit later, but let me get to really the way to refine this main question. So we care about learning graphical models with latent variables. That was the question I was motivating since the beginning. And maybe the more refined question is, can we do better than n to the d time? So can we hope for algorithms that, like in the case without latent variables, they run an f of d times poly and n time? That's the goal. That's our goal, is to design these type of FPT types of algorithms. And n to the d time is actually kind of trivial for reasons that I'll get into later, because it corresponds to a type of brute force search, which is really the sort of naive baseline. So let me tell you about our results before I'll roll up my sleeves and we'll get into some of the technical ideas. So first, let's talk about the representational power of restricted Boltzmann machines. So one direction I told you was folklore, that if you take a restricted Boltzmann machine with bounded degree and you marginalize out these unobserved nodes, you end up with a Markov random field. But actually, the pretty surprising thing is that the converse is true too, that if you take any Markov random field, you can actually realize it as a bounded degree restricted Boltzmann machine. So the theorem is that every binary Markov random field f of order t can actually be realized as the distribution on the observed nodes of some restricted Boltzmann machine where the maximum degree of any hidden node is at most t. So this is actually a complete model for this class of Markov random fields. So this gives, in a sense, a very precise characterization of the representational power of these bounded degree RBMs. And in contrast, the things that were known before really required much larger degree. So for example, there was a work of Martins et al., where they showed that RBMs can be really rich. They can represent things like parities, or more generally, predicates that only depend on the number of ones. But the catch was that the degree was actually linear in the number of variables, which doesn't really tell you anything about the hardness of learning RBMs with bounded degree. But once we have this equivalence between Markov random fields and RBMs, we get a lot of striking results about the hardness of improper learning as a corollary. So for example, under the sparse parity with noise assumption, it turns out that then it's hard to learn any representation on the distribution on the observed nodes that's, say, close in total variation distance 1/3 in time better than n to the order d. And here it's even a very weak notion of learning. You can even do it improperly, where you just allow your algorithm to spit out any unnormalized function that can be computed efficiently. This problem is still hard. In fact, things get even worse, because not only does our reduction, from MRFs to RBMs produce bounded degree, but if you start off with a Markov random field that represents the sparse parity with noise, you create an RBM that not only has bounded degree, but it has a bounded number of hidden nodes. So it turns out that learning an RBM, even in this weak notion of improper learning, is hard for constant degree with a constant number of hidden nodes. So that stinks. And in comparison, a lot of the earlier works, they required a huge number of latent variables, things where the number of latent variables was linear or even larger than the number of observed nodes. But maybe the better question, since I'm more of an algorithms person, is, all right, so maybe we were too optimistic. We can't really hope to learn RBMs without any assumptions. But are there still some sort of well-motivated and natural families of RBMs where we can do much better than n to the d? And the answer is yes. It turns out that if they're ferromagnetic, namely if the interaction matrix and this vector of external fields are non-negative, then we'll be able to give exactly these kind of strong algorithmic results. So there's a long history of study of ferromagneticity. It plays a key role in classical statistical physics, theoretical computer science. And these types of models then have applications to things like the spread of innovation on social networks is one place they've used. I'll skip this, but you can ask me afterwards. But let me tell you about the main results, which I want to get to. So our main result is that there's a simple greedy algorithm which runs an f of d times poly n time with sample complexity f of d times log n, which learns ferromagnetic RBMs. But again, you need these upper and lower bounds on the interaction strength to do so. In particular, what does learning it mean? So we output a description of the joint distribution on the observed nodes as a Markov random field. So there's a fairly strong notion of learning. In fact, what's neat is under this notion of learning, well, you can actually use the model that you've learned on the observed nodes for downstream tasks like performing inference. For example, you can use these models to give a p-task for estimating the likelihood of particular outputs of your model. So I won't say any more about that, but really what I want to get into is some of the ideas about how exactly these ferromagnetic RBMs are so much easier than the general case of RBMs. And I'll also add that everything that I'm going to say is actually going to generalize to ferromagnetic Ising models, provided that you have bounds on how far apart your latent nodes are from each other. Okay, so let me roll up my sleeves and tell you about a really cool technical connection that was definitely news to me. So the way that we're going to give a simple greedy algorithm for learning these ferromagnetic RBMs is through analyzing the properties of this particular function, which is called the discrete influence function. So the way that it works is that we have some sort of graphical model, and we can think about pinning some variables in the set S to being +1 for the value. And we can look at when we pin those variables to +1, what the resulting expected, what the bias is of the corresponding variable xi. So the way to think about this function is that it takes subsets. These subsets are subsets of n minus I. And it asks, if I pin all of the variables in that set to +1, what's the resulting induced bias? So it's a function from subsets to a real value. And it turns out that this function has some pretty magical properties that are amazing. It's actually submodular. And even more amazingly, the properties that underlie its submodularity have actually been studied for a very long time in mathematical physics, but without explicitly making this connection to submodularity. So the main theorem which we're going to reason about is I claim that if we fix a ferromagnetic Ising model, then for every node I, this discrete influence function that I described above is a monotone function. It only increases in value when you fix more and more of the nodes. And it's also submodular in the sense that it has these rules of diminishing return. And it turns out that submodularity has really been studied in disguise since about the same time that it was introduced into discrete math, but it's been studied in mathematical physics, but it usually goes under the name of the concavity of magnetization. And it's really, in modern terms, it's related to what's called the multilinear extension. So let me tell you some beautiful and intuitive properties about these Ising models, particularly ferromagnetic Ising models. Now, the original reason they were introduced in physics was as a way to model macroscopic properties of materials. You do things like understand phase transitions, how the external field affects whether or not magneticity emerges as a global property of your material, but you model that material just with these simple pairwise interactions between each of the individual particles. Now, the thing that you might care about if you care about the physics applications are things like the average magnetization. So you can take your Ising model, you can look at the expectation of the sum of all of the spins, and you can divide by n. And let's assume that this interaction matrix is non-negative, so that it's a ferromagnetic model. Let's assume that the external field is the same value h everywhere, and that h is non-negative. Then there's some really intuitive and classic results that go back to the 70s. One of them is that if I take something like the average magnetization and I increase h by a small amount, the external field, what should happen to the average magnetization? It should only go up. So this is really a statement about the partial derivative of the average magnetization as a function of the external field. It's non-negative. But in fact, there's a more remarkable property, which is going to be the key to our algorithm, is that magnetization should also have this law of diminishing returns. If you think about starting from two external fields, h1 and h2, and h2 is much larger than h1, well, if you increase h1 a little bit, you look at the change in the average magnetization and increase h2 by the same amount. Well, since h2 was bigger to start off with, you should increase the average magnetization less. So that law of diminishing returns is captured by the second order partial derivatives of this average magnetization, which is why it's called the concavity of magnetization in mathematical physics, is because the average magnetization is actually a concave function. And it's related to things like the Griffith-Hirsch-Sherman inequality, which captures exactly this notion of diminishing returns. And it'll turn out that mathematical physicists were studying this property in the 1970s. Discrete mathematicians were studying submodularity in the 1970s, but they actually talk about the same thing when it comes to ferromagnetic Ising models.
Oh, can I ask a question here?
Yeah.
So the external bias, this h, that's constant for all of the.
Yes.
Okay, great. So, but it's not a vector yet.
It's not a vector yet, but it turns out that based on a method that, the actual GHS inequality, we'll actually be able to see this as one consequence of GHS, and submodularity will be another consequence.
Where it's like partial hi, partial h.
We're getting there. That's exactly right, but we're getting there. Great. So let's try and dig into it. Now, let's take submodularity for granted, and let me convince you that there's a simple algorithm for learning these ferromagnetic RBMs, because it'll just come from assembling a lot of simple observations. So, at the end of the day, the thing that I care about is learning ferromagnetic RBMs, which have latent variables, right? I talked about the discrete influence function of a ferromagnetic Ising model. But, if you have this discrete influence function for a ferromagnetic Ising model is submodular, then so too is the corresponding influence function when I look at something with latent variables. Because what I'm doing is I'm taking this nice monotone submodular function, and I'm just restricting what kinds of subsets you're allowed to plug in to the function, because you can only pin the observed nodes. But now this discrete influence function inherits all of the nice properties of the function that I had before. So that's great. Now, here's the key idea, and this is the thing that I'll reason about with a picture for you, is that this discrete influence function, the reason it's going to help us learn ferromagnetic RBMs is because what I claim is that the maximizers of the discrete influence function are nice and reveal important properties about the graph theoretic structure. See, what I claim is that they ought to be the two-hop neighbors of some node. So if we think about our RBM, and we think about some node I, and I care about its bias. Well, if I can only talk about pinning any of the observed nodes, the question is, what observed node should I pin to have the most influence on the underlying bias of this node? And the answer would be all of the nodes that are distance 2 away from I. Because once you condition on these nodes and you pin them to +1, then all of the other observed nodes are conditionally independent. So they no longer have any other influence on the bias of I. So that's the key point, is that if we can actually find the maximizers of this monotone submodular function, then what we should have is we should have an idea about who are the two-hop neighbors of this node I. So the two-hop neighbors exactly because they act as separators. So the formal statement is that if we have these sort of alpha beta non-degeneracy conditions, namely we have lower bounds on the strength of any non-zero interaction, and we have upper bounds on that essentially control how biased individual nodes can be, then the quantitative statements, and I should mention that you need some conditions like this to make the graph theoretic structure, even for an Ising model, identifiable. But in that case, the thing that you can prove to make some of this intuition precise is that if I take the discrete influence function for some node I, and I look at a subset S that does not contain all of the two-hop neighbors of I, then I can do better. I can make the discrete influence function larger by some quantitative amount that depends on these non-degeneracy parameters. So that's the key point. And now we're in good shape because the main question is, how can we try and maximize this discrete influence function? Well, actually, also since the 70s, we've studied things like maximizing a monotone submodular function subject to a cardinality constraint on the set that we plug in. And there's this classic work of Namehauser et al., where they give a 1 minus 1/e approximation algorithm. Now, that's not quite good enough for us, but actually, their analysis tells you something a little bit stronger than that, because it's a simple greedy algorithm that keeps picking a new variable to add into my set that makes the most progress on my function. But it turns out that you can actually use their analysis and turn it into instead a bi-criteria approximation algorithm. Namely, it's going to achieve an approximation factor that converges to 1, but at the cost of looking at larger sets that expand the cardinality of the thing you're competing with. And now what you can do to turn this back into this algorithm for learning ferromagnetic RBMs is you take your discrete influence function just restricted to the observed nodes. You start from some node I and you keep greedily adding other observed nodes that increase the discrete influence function. And eventually what you're going to do is you're going to learn a superset of the two-hop neighbors. Why? Because if you haven't learned a superset of all the two-hop neighbors, there's another node that should make a lot of progress, and then it violates your approximation algorithm constraint. So that sounds like we're almost done, because instead of learning the two-hop neighbors, we've learned a superset of the two-hop neighbors. But then we can use a lot of standard techniques just to prune that down, because we've reduced down to a constant size subproblem. So once we have monotonicity and submodularity, the problem is easy. We get our efficient algorithms. But now let's talk about why these things are actually submodular. And this part is pretty mysterious. So actually I have to work with something a little bit different than the discrete influence function. There's another nice thing you can do, which is you can look at something that's called the smooth influence function instead, where the idea is that instead what you're going to do is this influence function looks at the expected bias, but what you do is you change the external field, H. So in particular, you can recover the values of the discrete influence function, because if I think about how to mimic the effect of pinning all the variables in S to the value +1, I can accomplish that just by taking the external field and setting the external field for all of the nodes in S to plus infinity, because that pins them to the value +1. So this is just the continuous extension of the discrete influence function, but it'll be easier to work with things like the partial derivatives of this influence function, even though it contains all of the old information. And in retrospect, this is really in the language of submodular functions, this is what's called the multilinear extension. So, I probably should show you what the Griffiths-Hirsch-Sherman inequality is. It's this monstrosity right here. Does anyone have any intuition for this? Not Freddie. Freddie might. No? Okay, well, clearly you can see that this implies the property we wanted, so we're done. Actually, I don't have very much intuition for this, but it's used, this technique, there's a very important technique called the random current method, which is used to prove it. But the important thing is really that it's related to proving these bounds on the partial derivatives that I talked about earlier. So in particular, the GHS inequality can be used to prove this fact that I gave you before about the concavity of magnetization. In fact, it can prove another related statement, which is if you look at the partial derivatives of the smooth influence function, but where you vary the external field at J and K, then that has the same type of law of diminishing returns where the second order partial derivative is non-positive. So that's the important thing. In fact, there are other related inequalities, in mathematical physics, things like if you look at the covariance between two different nodes, well, since it's ferromagnetic, you sort of expect that these should be non-negative. And this is related to some of these other properties, like showing that the smooth influence function, its partial derivatives are all non-negative. But now we're in good shape because we're going to take these things which are corollaries of the GHS inequality for granted, the statements about these partial derivatives, and we're going to prove submodularity, and then we'll be done. So how do these properties about the partial derivatives of the influence functions imply that, in particular, the discrete influence function is monotone and submodular? And essentially, the proof is by integrating. So let's do it in a simpler case. We just want to prove that this discrete influence function I defined earlier in the talk is monotone as a function of a set S that we're pinning to the value +1. And the idea is that, let's take some external field H, and let's add in something to make all of the corresponding external fields to the set S be pinned to +infinity, so that they get pinned to +1. And then the idea is that we can look at what happens to the influence function when we add in the variable J into the set S and compare it to what happened before. So here what we're looking at is how much does adding in the variable J and pinning it also to be +1 affect the bias on the node I. So in particular, we can turn this into just the integral of this partial derivative, because what we're in effect doing by adding this node J into the set S is we're just pinning its external field to be +infinity. So we can think about this as really just integrating all of these little changes in the external field when we increase it all the way to infinity so that it also becomes a pinned variable. In that case, we're in good shape because we know from this Griffiths inequality that all of the terms inside the integral are non-negative. So in particular, it implies that the difference between these two discrete influence functions is also non-negative. And that gives us the monotonicity property, right? That pinning more nodes only positively affects the bias of any other node, at least if you're in the ferromagnetic setting. And the proof for submodularity is basically the same type of argument. You fix two different sets S and T. You can talk about these modified external fields where I pin everything in S to +infinity. I pin everything in T to +infinity. But what I want to do is I want to prove some type of law of diminishing returns. So I ask, how does the discrete influence function change when I add J into the set? I can write it out as the same type of integral. But now the key point is that I can lower bound it instead by changing the external field from H prime, where S is pinned, to H double prime, where this larger set T is pinned. And the reason I can go from one to the other is because actually, the second order partial derivatives are all non-positive. So as I change everything inside the integral, I'm only going to decrease it. But now we're in good shape because the right-hand side is literally the difference between the discrete influence function when I add j in to the set t and I leave it out. So this proves exactly this law of diminishing returns that is related to things like the concavity of magnetization. So let me quickly give you a summary, and then I guess it's lunchtime. But the main things that I wanted to get across is that there are some very interesting questions, even if you take some of the classic problems about whether you can learn graphical models, and you ask the same type of algorithmic questions, but with the twist about what happens if there are latent variables instead. That can make the problem much more computationally difficult. A lot of things which we know and love in the case without latent variables, like learning graphical models with bounded degree, that stuff does not carry over to the case where you have latent variables, because then you get much worse hardness results, things that tell you you need end of the D time. And the way that we proved this was through this precise characterization of the types of distributions that can be represented as bounded degree restricted Boltzmann machines. That gave us these lower bounds, not only for learning bounded degree restricted Boltzmann machines, but even with a constant number of latent variables. But that doesn't mean that the game is over, because there still can be very rich models of RBMs, which we can beat these type of end of the D bounds. And I gave you a simple greedy algorithm based on submodularity and the concavity of magnetization for learning ferromagnetic RBMs. But I think this is very much a story that's still to be written. I think one of the main open questions is really to identify other tractable classes of latent variable models where you can beat these types of end of the D guarantees. So I'll stop there and a few minutes for any questions you might have, but thanks for your attention.
Yeah, thanks for the talk. I was wondering if you could comment at all on the relationship between the approach you're taking and the kind of, there's like the statistical literature on learning Markov random fields. A lot of that has kind of historically focused on continuous random variables like Gaussian or Gaussian populist kind of thing. But there's also versions of it that are in your kind of more binary space. And the important difference is that often there the focus has been on using the pairwise Markov property or exploiting the pairwise Markov property to learn the structure of an MRF. So where you have like x1 and x2 and you condition on all other variables in the set. And I guess, there's like statistical issues with that, but like complexity wise, how does that relate to what you're talking about?
That's a great question. So for example, there are some really beautiful works about taking, let's say, Gaussian graphical models and marginalizing out some of the nodes and then asking whether you can, find some sort of parsimonious explanation, maybe in terms of the precision matrix being sparse, right? Now, those all rely on the property that if you marginalize out nodes in a Gaussian graphical model, you get back a Gaussian. So the big issue is that for things like these Ising models, as soon as I marginalize out, I create a higher order dependence. So that property of having only pairwise interactions be preserved under taking marginalization seems to be a very specialized property.
Yeah, but it doesn't. I agree with what you just said, but there's also procedures that allow for general Markov random fields. So like look at cliques in the way that, so in this literature, it's in terms of like clique potentials instead of pairwise interactions. But still the pairwise Markov property holds, even in a higher order MRF. If two variables are not adjacent, then they're independent conditional on this one set, which is the set of everything else.
Yeah. But there, for example, one of the big questions is also what happens to the computational complexity of those types of things. Because if we define it with clique potentials, so sparse parity with noise is a very, very simple Markov random field with very small order too, because it just depends on the sparsity T. So one of the big issues is that, sparse parity with noise is hard. That imposes some pretty strong lower bounds on the computational complexity of things, even if you can represent them in terms of clique potentials. But maybe there could be cases where you could get around that. I don't know.
These influence functions that you have here, they're defined in terms of these expectations. And I think I think if I'm following right, these expectations you're able to approximate because they're the samples that you've
Exactly.
seen. So let's kind of like an intuition on, well, this function is submodular, but I only see it with samples, and I have to sort of combine many different like greedy algorithms. What's sort of the intuition for how to piece this all together?
Yeah, that's a great question. So, the important thing is that once, the hard part for things like Markov random fields is figuring out which other nodes are in your potential, like in your hyperedge. So the important thing is, the way that we're learning it is we're learning a Markov random field on the observed nodes. But once we've, done these greedy algorithms around each node, we've drastically pruned down which are the other nodes that could participate. So then there are a lot of other standard techniques you can do once you're down to a much more constant size problem. But it's not so clear that we have the right way of combining all of those things. There definitely could be more clever ways too.
Yeah. So is similarity is the necessary condition for this approach to work? Like if you have an inflation factor equals just monotone, but not submodular.
Well, so here it's a maximization problem, which is cardinality constrained, because you wouldn't want to put the entire subset in there, for example. But one of the issues is that if you're trying to maximize a cardinality constrained monotone function, and it's not submodular, then it's very difficult to say something non-trivial. So if you think about, for example, the RBMs that come out of the sparse parity with noise type of reduction, they'll have this property that there are a few other nodes that once you find them, you can affect the bias of this node that you care about. But until you find all of those other companions, you don't have any effect on the bias. So one of the big issues is that without some kind of property that prevents you from making all of your progress in one last step, it's very hard to know how you're going to make progress towards maximizing whatever influence function you care about. So it's not necessary for this algorithm to work, but it's also not so clear what's another way to articulate some interesting class of models that evades what goes wrong with the sparse parity with noise examples, where everything happens at the end and you end up with a brute force search to figure out what are the companion nodes.
So if I understand your results correctly, you're essentially trying to do proper learning of an MRF for the marginal. Can you say anything about what's happening in the Licking space?
That's a great question. Another interesting open question is whether or not you can actually learn a ferromagnetic RBM and actually find a ferromagnetic representation. So here you can go the other direction. Once you have the Markov random field, you can translate that to a bounded degree RBM, but it won't be ferromagnetic anymore. So in fact, when you think about, this is the part that I sort of glossed over, but one of the reasons people care about ferromagneticity is it actually enables things like efficient sampling, for example, for the Jerram-Sinclair result. So in fact, there are a lot of things that you can do with the ferromagnetic representation if you can learn it, but we learned something that's not necessarily ferromagnetic as an RBM. But still, we can use these things that are called Li-Yang properties because it inherits a lot of the nice properties about the partition function. So we can still do other things like be able to efficiently perform inference, but sampling would be an open question.
I think all remaining questions should pester Ankur at lunch. So thanks a lot. Back here at 2 p.m.